Right. Hello, everyone. Thanks for the introduction. My name is Feng. I'm a co-founder of Veritize, a new startup for blockchain security. I'm also a CS professor at UCSB, in which I run a lab for doing verifications for security. And so today I'm going to present our ongoing work for applying formal verification for ZK circuit. And this is also a joint work with my student Yanji, who does most of the heavy lifting stuff. Unfortunately, he cannot be here because of visa issue. So before we get started, so what's formal verification? For those of you who don't have much background on formal verifications, so essentially the goal of formal verification is essentially to construct rigorous mathematical proof that a given applications behave as intended, right? So your given application can be your DeFi smart contract, can be a ZK circuit. So which means that, so when we say formal verification, essentially take two inputs. First, the source code of your program, as well as a formal specification, which essentially encode what's the intended behavior of your desired target. And then, so when you run formal verifications over your program and the spec, so it's going to generate two kind of a different outcome. Either it's generate a mathematical proof. In this case, it certify your program is correct with respect to the spec you provide, or it generate a counterexample showing that the edge case that you didn't satisfy, okay? And so just like when you are doing mathematical proof in your elementary school, sometimes you cannot make the proof proceed, and then you might get help from your teacher. So in this case, occasionally, so for formal verification tool, you might also get like actual human expert input for some domain knowledge that you don't, it is not accessible by your formal verification tool. So you might wonder why this matter, right? Why do people care about formal verification? Because it provides the highest level of assurance over the behavior of your software artifact compared to ad hoc approach such as testing and or manual auditing, right? In the sense that it actually ensures all the edge cases are considered using rigorous mathematical proof. And so why this matter? Because for instance, all of you probably know the recent hack from Beanstack. And for instance, even though like all those kind of DeFi applications, they feed a huge amount of money to those auditing companies, they're still getting hacked like every month. So, and the reason is that existing auditing process, they actually fail to reason about all possible behavior of your artifacts. So now it comes to formal verifications for ZK circuit. In this case, we use like a ZK circuit in terms of R1CS as an example, but the idea can generalize to basically ZK circuits in arbitrary intermediate representations that you might be familiar with. So in here, I'm going to reuse the example that you saw from Ignis example, in the sense that you have a circuit on the left-hand side, which is essentially a set of polynomial equations. Okay? So in this case, so you just need to understand that there is a couple input, x1, x2, x3, as well as some intermediate, what they call witness variable, I1, I2, I3. And then the circuit essentially is going to produce an output y. Okay? In this case, I want to verify this circuit. What do you mean by you verify this circuit, right? So in this case, what you want to verify is that first, it is correct with respect to certain spec, okay? In this case, let's assuming that we use the original SOCOM program to represent the spec of the desired behavior of your circuit in R1CS, which is essentially on the left-hand side, okay? So when we say we formal verify a circuit, in this case, we concern about two properties. The first property is about equivalence. So the equivalent saying is that, for those of you who might not familiar with first-order logic, is that this is essentially a universal quantifier. What you quantify is that for all possible space of your input, you want to assert that the program on the left-hand side, as well as the program on the right-hand side, they should always return the same result, okay? No exceptions. And then, so that's equivalence property. And the second property you also concern is essentially the uniqueness property that can be handled by Ignis, in the sense that right now, I'm concerned whether my programs, my circuit on the right-hand side can potentially violate the notions of uniqueness. What do we mean? In the sense that in this case, so you're going to use a query with existential quantifier in the sense that, well, can you actually give me two different kind of like a witness variables such that it satisfy your polynomial equations, but they actually different with each other, right? In this case, you make a query to the solver, and then if the solver return yes, which means that your circuit are potentially buggy because it violates uniqueness. So once we agree on the problem definition about what to verify, and then the next step is to how do we even build a verifier, right? So in this case, it turned out to be, in order to verify your program, essentially all you need to do is to convert your program into its corresponding mathematical representation. In this case, your mathematical representation is going to be a logical formula. And how do we do that? Here comes the design of our system called pickers. Okay? In this case, the system is going to take two inputs. The first input on the top left is essentially correspond to the circuit to be verified. Well, in this case, we use R1CS circuit as an example, but you can use, essentially the system can be generalized across arbitrary representation. For instance, you can replace R1CS with relaxed R1CS or some reason representation. It doesn't matter. Okay, so this is a circuit you want to verify, as well as a specification that you want to enforce that knows to denote the correctness of your circuit. So in this case, I'm just using its corresponding circon program as the reference implementation, but you don't have to. For instance, you can use a program in Leo, or you can use like arbitrary, like high-level programming languages to notate the reference behavior of your desired circuit. Okay, and then so once we have those two inputs, so essentially the core idea, the core of the verifier is essentially just two interpreter. Okay. So what those two interpreter does is essentially it's going to be interpreter for the corresponding target language that you want to verify. In this case, we have an interpreter for R1CS program. We also have an interpreter for circon. So interpreter is nothing special other than the homework assignment you might done in your compiler class, in the sense that if you fit interpreter with a concrete input as together with circuit, it's going to interpret your program and then generate a concrete output. So what's more interesting is that once you fit the verifier with your program with a symbolic input. In this case, this X corresponds to the input, and then you want to reason about the behavior of all possible X, okay, not just one certain X. So in this case, our verifier actually leverage Rosette. So the solver-aided programming language to lift executions of your interpreter into its corresponding formula. Okay? So we do the same thing for the circon program, which essentially turn into a mathematical formula which can be reasoned about using off-the-shelf solver. Okay? So in this case, the output of the system is going to be either a correctness proof to certify that your program is correct, or it's going to generate a counterexample to demonstrate that such that those two programs actually behave differently. Okay? So here I want to mention that the design of the framework is actually highly customizable in the sense that the core implementation is just two interpreters for R1CS and circon, and then you can essentially replace your interpreter with arbitrary intermediate representations or programming languages. And it turned out that, so when we build the framework, and majority of the effort is actually spending on, because of the poor documentation in circon programming languages. And at the end, we actually faithfully follow the semantic of R1CS and circon semantic, which actually leads to both good news and bad news. The good news is that this is actually close to some sort of like a real usage prototype in which you can apply to your circuit. And then the bad news is that it leads to some challenges. And those challenges are actually not quite surprising to existing solver, because as you can see, the circuit we try to verify, most of them are essentially nonlinear operation, right? So basically, polynomial equations are just everywhere, which is essentially very, very bad for existing SMD solver. So in this case, what do we do? Shall we give up, or just develop a specialized polynomial solver? Okay. So the second challenge is that, so there's a lot of arithmetic operations over large prime number, as you've seen from Brian's previous presentations. And the last one is essentially like a scalability issues, in the sense that how do you even verify like a circuit from this project with like several millions of constraints, right? So in this case, I'm going to briefly illustrate our ongoing effort about the first two. And so I'm going to elaborate the last one with our future work. So for the first one, so because like nonlinear operations are everywhere, which is very, very bad for existing constraint solver. So what we do is that, but we still want to leverage SMD solver. So what we do is that we are going to model those expensive nonlinear operations as uninterpreted functions. So what do we mean by uninterpreted function, in the sense that I don't care whether it is modifications or mod operations. I just treat it as a regular function, okay? So which means that in this case, let's take a look at this example. Probably the font size is a little bit small. So in this case, I have two functions, Feng1 and Feng2, and obviously those two functions are equivalent. So essentially, you just square the parameter, okay? Where the first one, essentially, it do some like intermediate movement about those data. So in this case, I want to prove the equivalence of those two functions. So what you do, essentially, you just traverse every single statement of your program, and then you translate into its corresponding formula, and then at the end, so you want to assert that where those two programs are equivalent, right? Which is essentially equivalent to asking whether there exists an input such that those two return different value. And then it turned out that even with those simple like verification tasks, if you just naively fit to the SMD solver, it takes over 5 minutes to terminate. And then one of the reasons is that, so the solver has to actually concretely reason about the behavior of these modifications. And it has to exhaustively search the space of all possible solutions to give you the answer. Whereas if you treat these functions as uninterpreted at the bottom, in the sense that it's just a function, which means that what does function do, in the sense that if you just give me the same argument, I'm always going to return the same result. That's it. And it turned out that if you model as an interpreted function, it can give you return the answer in a fraction of seconds. However, there's no free lunch. When you like do this kind of uninterpreted functions model nonlinear operations, there's going to be a trade-off in the sense that you might generate false positive. Okay? And then, so I'm going to elaborate like the trick that we are going to do to illustrate this problem. So now I'm going to talk about the second trick that we do with challenge 2, in the sense that there are like essentially arithmetic operation over large prime everywhere. For instance, this is the documentation from Circon programming languages, in the sense that for every binary operations, it will always apply a mod operations over the operands over a large prime number, okay? So which means that internally, so the Circon compiler is actually maintaining some variance or rewrite rule like the following, which is not accessible by the SMD solver. That's why it has a very, very hard time to reason about. That's why it has to try all possible like computations to see whether there's a counterexample. In this case, what we do is actually pretty simple in the sense that you can think of, we design a theory of prime in the sense that we encode this kind of rewrite rule as actual axioms to fit to the SMD solver, and then let the SMD solver to aware about those kind of equivalence of those rewrite, such that it can actually reduce those kind of complex prime operation into its simpler form. Okay, and does that even work? So what we do is that we actually evaluate those our two on the same benchmark from IGNI, which contain most of them from Circon. And we use a timer of 2 minutes. You might wonder, so why do you use 2 minutes? So if you can verify a large circuit, I'm happy to wait several hours or several days, right? And the reason is that because so we are actually working on this actually at the last minute. So just to get results, actually like 10 minutes before my talk, like Yanji was still making push. So that's why you can think of what I'm going to present, you can think of it as the lower bound. It's essentially the lower bound of the verifier. And then in this example, since you already see the result from Franklin's presentations, I'm going to only focus on equivalence checking. And then, but our tool do provide like a built-in support for uniqueness. It's essentially just a different query you're going to send to SMD solver. So the result is not as shiny that you can like present in a, let's say, top tier academia conference, but it still like shows some encourage like information in the sense that among those data set, so even with 2 minutes of timeout, we can already prove like 32% of the circuit. And you might wonder what's going on with the rest of the benchmark that you cannot prove, right? It turned out that there are multiple reasons. The first reason is, of course, scalability. Like, for instance, what happens if your circuit has millions of constraints, right? And then the second limitation, the second reason that we cannot prove is because of earlier I made this kind of assumption in the sense that for all nonlinear functions, I'm just treating as uninterpreted. So which means that for some circuit, they are obviously correct and equivalent because of those like over approximations. So it's essentially you fail to like verify and then you generate false positive. Okay? So now I'm going to talk about, briefly illustrate some ongoing future work that is essentially driven by the limitations. Okay? So it's essentially, so the first one is about the specification language for ZK. Okay? And then the second one is like how do we design scalable yet precise algorithm to verify like larger circuit. And the last one is, the third one is about modular verification for large circuit. And finally, what we want to do is that how can we go beyond R1CS and SIRCOM, let's say for those programs written in Prong. Okay? So for the first one, so one thing that we realize that it's very urgent. It's essentially we need a separate and then language agnostic specification languages to specify what kind of property do you want to verify. For instance, previously, in our current implementation, we are using the reference implementation from SIRCOM program, and which means that we are assuming that the behavior of the SIRCOM program is correct, which is not. For instance, in this case, this is actually a bug report by Tornado Cache team in the sense that for this SIRCOM library, so the developer actually, instead of originally, it was supposed to use let's equal, it used equal. So which means that in this case, if you use this program as your reference spec, then you're going to like generate bogus result. Okay? So, and that's the first direction that was mentioned. And then the second direction, which essentially how do we apply like a more scalable algorithm for circuit verification, especially to deal with this kind of nonlinear functions. So as you probably remember, so when we want to reason about the program, I made some over approximations, which is like imprecise, but in my works. However, so let's say right now I want to perform verification, right? So I want to verify, let's say, Brian and Yi, they are equivalent in the sense that they are the same person. So which means that one naive way you can do is that you formalize Brian as a mathematical representation, right? Which is impossible. So even you can formalize like Brian as a mathematical representations, there's no way you can reason about like your formula. So what do we do is that if we can actually use a standard tree from the verification community in the sense that we can do abstract refinement. In the sense that, let's say at the very beginning, we reason about Brian and Yi using an abstraction of gender, right? In this case, you cannot differentiate those two because this abstraction is not sufficient enough. So which means that if you generate a counterexample, to show that right now, sorry, I cannot differentiate it. So in this case, you can actually further refine your current abstract refinement in the sense that, well, in addition to reason about gender, maybe we can reason about the color of the code that they're varying today, right? Which is sufficient enough to differentiate those two. So as you can see, so you don't necessarily need to reason about the complex behavior of your software system. You just need an abstraction that is sufficient enough to achieve your proof goal. So as you can see, these iterations will keep iterating. Either it returns yes, in the sense that I cannot find any counterexample to dispute your argument, or I'm going to say that I failed to prove your system, which essentially indicate that your system might be unsafe. And the last one is actually pretty straightforward in the sense that, let's say, once we spend a lot of effort verify those individual circuits, so for those like big circuits of million lines of constraint, what you can do is that it's essentially just like when we play with Lego, right? In the sense that for every circuit that we already verify, we essentially write down its summary in terms of the input-output behavior. So which means that and we already verified that we know that it is safe. So which means that when you reason about like a larger circuit, it's essentially just a matter of stack those summary together. Okay? That's essentially all the presentations. And then if you have any questions, feel free to reach out to us using our first name at verydice.com. And so you can also access the prototype using the barcode. So one thing I want to mention that so this is still like a ongoing, very preliminary work in the sense that this project is not even a thing like a month ago. So I highly encourage you to check from time to time because we are going to put a lot of manpower to make rapid progress in the next few months. Thank you, and I'm happy to take questions.
With the specification language basically being CIRCOM and the verified program being the R1CS representation, does this basically, it feels more like a test of the compiler than it is a test of the code itself?
Yeah. So in a sense, in this case, you can think of you're trying to testing the correctness of your compiler, right? But like if you replace the CIRCOM program with the actual specification that you want to enforce, it's essentially a verifier, right? So as I show you in the figure, so we don't necessarily need to buy to the CIRCOM programming language.
Interesting.
Yeah.
Hey, thank you for this talk. This is actually very interesting to hear because I do some work in formal verification of EVM circuits. Two quick questions. First one, at a high level, could you give some quick intuition as to why, even though the equivalence spec is based on this universal quantifier, which Z theory is notoriously bad at handling, how you guys are able to still get it to work?
So you mean how do we get Z3 to work with those kind of constraint in circuit? Is that your question?
Right, or at least on one of the slides I saw there was a universal quantifier for describing the equivalence between two circuits. Is it that at some point you remove the universal quantifier?
So there's a standard trick in the sense that if you want to, the reason that you have this kind of universal quantifier is that you want to prove the validity of your argument, right? So that's why you need this universal quantifier. And then there's a very standard trick in the sense that to prove the validity of your formula, it is equivalent to check whether the negation is satisfiable. Okay, so which means that in practice, to get rid of the universal quantifier, all you need is essentially just put a negations on top of a formula, and then you can essentially use existential quantifier.
Gotcha. Okay, thank you. That makes sense. And then the second quick question is, have you looked for, or does there exist theories on prime modulus operations? Because I know it's not natively supported in Z3, and it seems like you guys have to do this weird modulus stuff, which can result in errors of unknown sometimes. So yeah, what is the thing you process there?
So the short answer is no. There's no existing theory for prime. Right now, the existing theory for Z3 that works very well is linear arithmetic, big vector, uninterpreted functions, and the limited amount support of string. So right now, what we are working on, essentially, we are working on the theory of prime. And then the one that I show you, essentially, very, very preliminary result. And we are working on the rest of the fragment of the theory.
Awesome. Super cool. Thank you.
Thanks for your talk. What difficulties do you foresee when trying to verify Planck? Is it just larger polynomials, or what do you think will be difficult?
The larger polynomial is definitely going to be a problem. So everything become bigger, it become nasty to reason about. So which is not specific to a ZK, right? It's essentially applied to every software artifact. So I think one thing that is specific to ZK verification is that, so it's about the operator, especially for those crypto primitive operator. So they are actually involve either super nonlinear functions or include a very complex hashing functions. So which will create a lot of trouble to the constraint solving. For instance, we observe that even like some small verification tasks, they might generate simple, like smaller constraint, but it's actually very difficult to solve.
Thank you.
Okay, thank you.
Thank you.